Perot and his running mate was Admiral Stockdale, and they had the vice presidential debate, and Stockdale got up and said, "Who am I and what am I doing here?" So I think I know who I am, but what am I doing here? I'm not quite sure. I don't work in this field very much, and so I was hard-pressed to try and come up with something to present. And but I realized that in this audience, it's refreshingly much younger than I am, and I thought maybe it'd be useful for you if I gave an overview of just pure aggregation kinetics, because it's a well-established field, but on the other hand, there's a lot of beautiful techniques for understanding the behavior of the evolution of the cluster size distribution. And then at the very end, I'll try and say something to make me like a discussant to try and, tie in with some of the things that I've been learning about today. So here is the basic process of aggregation kinetics. You have a cluster of mass I, a cluster of mass J. They come together at some rate, which is given by a reaction rate K sub ij, to form something which is even bigger in a mass-conserving way, so it's of mass I plus J. They just add up. So this is the basic process that I want to try and illustrate some of the basic phenomenology. So there's a long laundry list of people who've worked in this over a period of like 80 or 90 years, and I've listed just some of them. And here is a couple of typical applications. Polymerization gelation. When you cut yourself, that's why you don't bleed to death, is blood coagulates. In astrophysics, we have formation of stars, formation of planets. There's always gravitational aggregation going on. When it rains, it's because we have water vapor that condenses into water droplets. We make yogurt by curdling milk. It's a long laundry list. So what I want to do then is present to you the master equation approach for understanding the evolution of the cluster size distribution. So our basic quantity here is C sub k, the concentration of clusters of mass k. And so here is the most important equation in the talk, and it describes the evolution of the cluster size distribution. So how does it change per unit time? And there's two terms that appear in this equation. There is a gain term, color-coded in black, and a loss term, color-coded in red. And so the gain term comes because you can have a cluster of mass I and a cluster of mass J. If their masses sum up to k, that will add to the creation of clusters of mass k. One needs a 1/2 here to correct for the overcounting, because I could create a 23-mer by 17 plus 6, or 6 plus 17. And then I should sum up over all combinations of I and J that add up to k. And similarly, there is a loss term because a k-mer can interact with anybody else of any size at the rate k sub I k, and that will contribute to the loss of the density of k-mers. So this is just making it a little bit more pretty, just to, again, say this is the creation term, this is the loss term. So this is the basic equation from which everything follows in the rest of this talk. However, there's a couple of really serious assumptions that go into this equation that are kind of, again, counter to like everything that I'm seeing in this workshop, but let me just outline them, and then again at the end of the talk I may have something to say about trying to make it more realistic. So first point is there's this notion of spatial homogeneity. That is that I'm writing here cluster concentrations without paying any attention to their spatial location. So I'm assuming a perfectly mixed system, so the concentration locally is the same as the concentration globally. Another feature is a little bit more implicit, but there's the only degree of freedom here is the size of a cluster. There's no notion of shape dependence or anything like that. So these two features together mean that there's no geometry, which I guess is just the complement of what's happening in this workshop. Also, there's the assumption of bimolecular reaction. That is, it takes two to tango, but we don't have a threesome coming together. And so this is something which happens in the low density limit, which is reasonable if I'm dealing with an irreversible process and the density of clusters is going down.
So no fission or evaporation?
Yeah, I'm assuming here no fission evaporation. These are things that could be put in, and in fact have been put in, and I'm guilty of that myself, so yes. And the other thing is I'm looking at the continuum limit, so this is a set of continuum equations, so I'm not including any kind of stochasticity because of small numbers of particles of a given size. So this is the thermodynamic limit. So these are the assumptions that go into the master equations. Okay, So in order to make progress, we have to specify the reaction rate. So let me now deal with that, and then we'll work with some generic examples of the reaction rate and discuss their solutions. So first, as a pre-introduction, let's talk about the simplest situation of the diffusion-controlled reaction, in which I have an absorbing sphere of some radius, and I have diffusing particles around it. Whenever they hit the sphere, they are absorbed. And so a basic question in chemical kinetics is, what is the reaction rate? And so what you have to do then is you have to solve the diffusion equation in this system where you have an absorbing sphere and constant concentration everywhere else. The system in 3 dimensions and above will go to a steady-state concentration profile. There will be a gradient of concentration at the surface of the sphere. One integrates the flux over the surface of the sphere, and with a little bit of work, and again, I don't want to belabor details, so I'm just glossing over everything here, but if one wants me to derive it, I'm happy to do so. One finds that the reaction rate is 4 pi dr. And just as a matter of sort of pedagogical amusement, this is kind of an amazing result, because you might think that when you have a sphere of radius a, that somehow the cross-section, the scattering cross-section, should be proportional to the cross-sectional area. And it's not. It's proportional to the length, the radius of the sphere, not the area. That's a very bizarre feature which has some very important ramifications.
So what's D?
D is the diffusion coefficient of the particles, yes. Thank you. By the way, if there's any questions, just shout them out. So when I'm dealing not with just like one absorbing sphere and just little tiny diffusing particles, but if I'm dealing with a gas of aggregates of similar sizes, then in the case of this aggregation process, it's sort of, one can take this and adapt it to this kind of situation of many different sizes of particles. So now I'm dealing with the reaction rate between a cluster of mass I and a cluster of mass J. If everybody's diffusing with their own diffusion coefficient d sub I and d sub j, it's the sum of the diffusion coefficients is the natural variable, and the natural radius variable is the sum of the radii. And so if these clusters are roughly spherical, or just not anything very pathological, then the radius scales as the mass to the 1/3 power, and the diffusion coefficient scales as the mass to the minus 1/3 power. So if you accept this, then you do a little bit of algebra. And now if one waves one's hands very vigorously and a little bit dangerously, you say, well, when it's in a large system, when there's a typical aggregate size I, then the ratio of typical size I to typical size J is 1, and so I'll just forget about it. This is actually a dangerous assumption, which is not really correct, but let's go with it as to develop like some simple models that we can solve and get some intuition. So anyways, that's...
Is that common to say the diffusion is the I to the minus 1/3 there?
This is if I'm dealing with spherical particles in some solution, this is exact. So I'm kind of making the assumption my aggregates are roughly spherical. So in hydrodynamics, this is a well-known result. Okay, so let me just tell you what are the exactly solved models of aggregation, because one can envision, because of all kinds of different phenomena, like in raindrops, one has to deal with turbulence and when bringing raindrops together. There's many different transport mechanisms, and so there's many different reaction rates that one can invoke. But these are the list of exactly soluble models is few and far between. Constant, we're going to solve in just the next slide. There's a so-called sum kernel, the product kernel, and this is kind of a science fiction-y kernel that's just a mathematical construct whose solutions are so bizarre that there are sort of two schools of study of aggregation kinetics, physicists and mathematicians. And so the mathematicians will something like this, will worry about this class of problems. Yes, so again, Ki is the reaction rate of a cluster of mass I with the cluster of mass J. Yeah, those are the only degrees of freedom that describe the clusters.
What would be the physical motivation for the product?
The product? Yeah, I'll tell you. Yes, I didn't pay you to ask that question. Okay, so let's first study the case of constant kernel aggregation. So now my reaction rate is, well, I've chosen my reaction rate to be 2. You remember there was a 1/2 here, and I got rid of it by saying Kij is equal to 2. And the reason for choosing a 2 rather than 1/2 in front here, it just makes the solutions look a little bit simpler. Okay, so how do we solve the system of equations? So you see it's a quadratic infinite set of equations. as an exercise to the interested student or interested listener, you could solve these one by one, because you can write C1 dot. There's no gain term of monomers. There's only a loss term. And you can solve them one by one recursively, and then you can start learning the whole plethora of tricks to solve these equations. Let me just show you the most elegant trick, which is the generating function technique. And the motivation for the generating function technique comes from the fact that this is the form of a convolution. In an elementary mathematical physics classes, you always learn that when you have a convolution, that when you Fourier transform, it turns convolution into a product. So similarly here, we don't have Fourier transform because we have discrete variables. So the analog of Fourier transform for discrete variables is the generating function. So if you've ever heard the term generating function, it sounds intimidating. It's nothing more than, well, it's actually the Laplace transform because it's one-sided, because we only have positive masses. We don't have negative masses. So imagine Laplace transform for discrete variables. And so let me define the generating function, which is summation ck z to the k. And if you're more familiar with the Laplace transform, you can think of this as the integral from 0 to infinity ck z to the power k. And it's just nothing more than the Laplace transform. And as we're going to see, if we make this substitution or use this fact, we can convert this system, infinite system of equations into a single equation that is solved pretty simply. So how do we proceed? We take our original master equation and we multiply each equation by z to the k and sum over all k. So on the left-hand side, you see that I just have exactly the time derivative of the generating function. This middle term, here comes the magic, because k I can write as I plus j. And so this is ci zi, cj zj, which is just the generating function squared. This constrained sum becomes unconstrained because I'm summing over all k. So I have two unconstrained sums, ci zi, cj zj, generating function squared. And similarly here, this is just the generating function with the 2. And this guy is nothing more than ci z to the power I when z is set equal to 1. So it's a generating function at z equals 1. So you simplify this to this. And this equation, so I'm not going to belabor things which are like sort of undergraduate mathematical physics, but let me just say that you can solve this equation. And so this is the solution. And then you can power series expand this in a power series in z to recover each of the cluster concentrations. And so this is the answer. So that's the solution to constant kernel aggregation. And if one looks at, looks like it's going to go off the edge. Anyways, so here's the exact solution. But this exact solution is not terribly useful because you don't see the scaling behavior. And so in the large time limit, if you the large time limit, you can factor out a 1 over t to the power 2 out in front, and then in the long time limit, that's just 1 over t squared, and then you have t divided by 1 plus t to the power k minus 1. And the long time limit, that just goes to e to the minus k over t. And that basically encapsulates all of the physical information in the cluster size distribution. So what I'm showing here is the cluster size distribution as a function of time for the monomers, dimers, trimers, 5-mers, 10-mers. And you see that in a long time limit, they all go to a common behavior, t to the minus 2. One can also look at the cluster mass distribution as a function of mass itself. And because of this exponential cutoff, one has like a plateau region, which is going like 1 over t squared. And then one has this exponential cutoff. And the point is that in this representation, it's easy to verify that the sum of the cluster concentrations scales as 1 over t, which is how the total number of clusters is disappearing from the system as a function of time. Yes?
Sorry, I'm confused by the x-axis. It says k, but then
That's
k,
right. Is the mass.
Oh, so it's not the subscript k on the c.
It is. I mean, C sub k is a concentration of clusters of mass k at time t. So k is the mass, concentration of clusters of mass k.
But then k is also varying with the different colored curves. C1, C2, C4s.
Oh, I'm sorry. What did let me table this because I've done something a little fishy here, but I'm not sure what it is. But thank you for the question. I'll figure it out. Anyways, let me now go to the product kernel, which is perhaps, so your question, why we even study the product kernel. One motivation for this is This is exactly the same as the Erdos-Renyi random graph in disguise. So most of you have probably been exposed to the Erdos-Renyi random graph as kind of a static process. You say, I have a bunch of nodes, I have a bunch of links, I ask, what is the geometry? But there's another representation which actually makes it the same as product kernel aggregation. So let's start with n isolated nodes, and let's imagine instead of saying I fix the number of links, I'm just going to introduce links at a fixed rate. So here I am, I'm introducing links at some fixed rate. And so I introduce, and at some point I freeze my movie. And the thing is that I am free as the user to choose my introduction rate to be anything I want. So let me choose it to be n over 2. The reason I'm choosing it to be n over 2 is that the number of links in the system at time t will be the rate at which I'm introducing links times the time. And so that's nt over 2. And then you can compute the average degree of the network. The average degree is twice the number of links divided by n, and that's exactly equal to t. So in this way of doing it, the average degree is just growing by, it's changing by 1 at a rate 1. So it's sort of a convenient representation. And so if one's interested in things like degree distributions, this is a nice way of representing it. But I don't care about that here. I'm more interested in the gelation transition, because this process, as you probably have heard from from like classic literature in Erdos-Renyi random graph, when the density is sufficiently low, you have a bunch of isolated clusters. When the density becomes high enough, there's a percolation transition where a giant cluster appears. Uttam talked a little bit about it yesterday. I'm going to now repeat those same results, but in the kinetic representation. So let's imagine looking at this Erdos-Renyi random graph at some intermediate stage. And so let's look at the green cluster and the purple cluster. The green cluster has mass I, the purple cluster has mass j. And I want to ask, what is the rate of creating a cluster of mass I plus j in this process where I'm adding links at some fixed rate? Well, the rate at which these two clusters merge is clearly proportional to the number of nodes in the I-mer and the number of nodes in the j-mer. So the merging rate is exactly proportional to ij. So this is nothing more than a realization of product kernel aggregation. And again, if I look at the concentration of clusters of mass k, it will evolve by our good old equations of aggregation, but the k sub ij is now equal exactly to I sub j, is equal to ij. And so these are now the rate equations. So this is why the product kernel plays a huge role in things like gelation, polymerization, and so on. Okay. So now, how do we solve this? So one can use the same techniques as the generating function techniques as constant kernel aggregation. Unfortunately, it gets a little bit black magic-y, and so I will just try and highlight the main points of it because it's so beautiful, the solution. So here are my master equations. I'm going to introduce the generating function, but now I'm calling generating function E. The reason E is because notice instead of multiplying ck by zk, I'm multiplying by e to the yk. Why do I do that? Because when I differentiate with respect to y, I bring down a factor of k, but there's not like a one less power. Like when I was doing ck z to the k and I differentiate, it gets z to the k minus 1. It makes the algebra a lot nicer when you do this exponential generating function. Notice also a k sitting out in front. You might say, why the heck did I do that? Well, it's just that when you've been around the block a few times, you realize that sometimes you want to engineer things before you start to make things look pretty. So it turns out that you could solve the same problem without the k in front here, but it's a little bit messier, so let me just keep it with the k in front. So now you take these equations, you multiply by e to the yk, sum over all k, and so here are the steps, and it's entirely mechanical. And the thing which is amazing, at the end of the day, when you work this all out, all the sums go away, you get things which involve either the generating function itself or derivatives thereof. You always get necessarily a first order PDE for the generating function. And the generating function equation that you get here is actually a very famous equation in mathematical physics. It's called the Burger's equation. So you might remember from like your experience with wave phenomena that d by dt plus d by dy of something, d by dt of something equals d by dy of something. That's just the one-dimensional linear wave equation. And you know what the solutions are. They're just propagating waves. Here, you have an epsilon e minus 1 in front, which means that the wave speed is proportional to the amplitude. So higher amplitude goes faster, you get wave breaking, and the breaking of that wave is what describes the gelation phenomenon. So anyways, this is the Berger's equation. It can be solved by the method of characteristics, which is a standard, thing that you get, and probably most of us have forgotten. I certainly forgot it before I started to learn it for this application. So you end up with this very pretty but very weird-looking implicit solution for the generating function. And now comes the black magic, which is that we want to. Here we have like y was our generating function variable. So we have basically y as a function of e. We want e as a function of y. We have to invert this function. And there is something called the Lagrange inversion formula. If you've never heard of it, it's going to look like black magic. And if you know your complex variables, it's just one of those incredible tools, the same as like residue calculus and summation of series. There's all these incredible tricks that come from complex analysis and residue calculus. And so here is the Lagrange inversion formula. And again, if one wants me to work out the details, I'm happy to do it. But if you haven't seen it before, this is black magic. Anyways, you end up with a very nice-looking form for the cluster mass distribution. It looks very innocuous, but it turns out that buried inside of this is something amazing happening. And so let's now look at the cluster size distribution or cluster mass distribution. Let's apply Stirling's approximation to get rid of the k factorial. And one finds that, in fact, it has an exponential cutoff with a power law tail. And so at time equals 1, it goes from, for short times, the thing is cut off exponentially with mass. But then at time equals 1, all this exponential factor goes away, and one has a k to the minus 5/2 tail, which is a sign of a phase transition at t equals 1. So for t less than 1, the system is just consisting of a bunch of finite clusters, and at t equals 1, they coalesce to give a percolation transition. One can compute the gel fraction, and so Uttam did it yesterday in a recursive way, and this is what comes up from the algebraic solution. It's the same equation that he derived yesterday. And the thing is that this equation has two classes of solutions. For t less than 1, the only solution is that the gel fraction, the mass fraction of the entire system that is in a single cluster, is equal to 0. And beyond t equals 1, one has the gel fraction is non-zero. And so here's the asymptotic behavior of this gel fraction that emerges from this equation. It's a transcendental equation, so you can't solve it analytically. You can only solve it approximately or numerically, and this is what comes out. So for t less than 1, there's no gel. For t bigger than 1, it's growing as t minus 1.
So this gets the correct distribution past t equals 1?
Yes. I mean, because here's the asymptotic behavior here. Yeah, so you can get everything you want beyond the gel point with this approach. Briefly mention the scaling approach, which is a very powerful way to infer general features of cluster mass distributions, knowing almost nothing about the process. So I'm going to make a scaling ansatz, which is very typical in statistical physics, which is saying that the cluster mass distribution, and because I'm going to the scaling limit, which is like infinite system size, I should treat my masses as continuous variables. So now x is the mass of the cluster, and cxt is a concentration of clusters of mass x at time t. And so we've seen that as time goes on, clusters grow, and there is some distribution that emerges. And it often is the case that the distribution is not a function of x and t separately, but a function of some scaled variable, x divided by a characteristic size of the system. So as the system grows, instead of using time as your variable, use the characteristic cluster mass as your variable and measure everything in units of the cluster mass. And so this is the scaling ansatz, and the prefactor in front is necessary to ensure that the total mass of the system is conserved. That is the integral of x, c of x. This should be constant, and that forces you to have this prefactor s to the minus 2 sitting out in front. And s, by definition, is the characteristic size of the clusters. Notice that x, c of x dx is nothing more, by definition, than the total mass in the system, and so is necessarily conserved. And so it's the second moment that defines a natural size scale in the system. So why do we do this scaling approach? So as I mentioned, we've reduced a two-variable problem to a one-variable problem. And in the case of aggregation kinetics, we have like a nonlinear integral differential equation that we can reduce into a single differential equation by the scaling approach. As you'll see, it provides the simplest route to asymptotics for all general types of processes. independent of initial conditions. It's a robust way of classifying aggregation kinetics. So in order to proceed, we need to say some general features of the matrix of reaction rates. And so there are two basic features that are necessary. One is the homogeneity index, which is that if I imagine multiplying all of my cluster masses by a common factor A, how much more rapidly does the reaction rate grow? And so this is defined by the homogeneity index. And then there's another index, which I'll call the diversity index, which is just when I take two clusters of very different masses, a monomer and a J-mer, how does the reaction rate scale with the size of the larger guy? So if I was dealing with constant kernel aggregation, this nu would be equal to 0, but it doesn't have to be equal to 0. There's a more geometric way of thinking about this, which is let's look at the entire matrix of reaction rates. And so up in the upper left, we have reactions of small clusters with small clusters. On the lower right, we have reactions of large clusters with large clusters. And here we have these reactions with disparate sized clusters. And it turns out that these two indices and this general picture, you can make a kind of classification scheme based on just these features. And it turns out, in general, in aggregation kinetics, there's three generic universality classes. The first case is when large interactions with large clusters and large dominate over everything. This is what happens in gelation, because if you think about, everyone knows about Jello. So Jello is multifunctional molecules, and so I have 4 arms, but I grab this guy, and now I have 7 arms because I actually have 6. But the thing is, and then we grab somebody else, we have more and more arms as we grow. We become so reactive that reactions of large clusters with large clusters dominate, and what's left behind, like they have so few arms, they don't react very quickly. And this is why you end up typically with a monotonic cluster mass distribution, because the very largest clusters are quickly removed from the system because everybody is so grabby, but the monomers left behind aren't very grabby, and so you end up with monotonicity. On the other hand, when you have reactions, these guys, the disparate size masses interacting very rapidly, one typically gets a peak distribution. And so why this occurs is that if I have a broad distribution and molecules of size 1 million react very quickly with molecules of size 1, then you won't have any molecules of size 1 because they're being reacted very quickly. And so you end up with a peak distribution. And then when all of these reaction rates are similar orders of magnitude, this is the marginal case where one gets very strange, non-universal behaviors that I may say something about at the very end. Okay, so let me just show you how you can apply scaling in a very productive way to infer the time dependence of the cluster, of the typical cluster size, with essentially no work. And when I say essentially no work, it's no work if you are kind of used to doing the scaling approach. People who work in the field of hydrodynamics, this comes like to them, this is their bread and butter to apply scaling. So it's going to look like work, but if you do this exercise once, you'll appreciate its power and you realize it isn't any work. So here is now the master equations for aggregation, now written in the continuum formulation. So here I have the gain term where a cluster of mass y and a cluster of mass x minus y come together to necessarily make a cluster of mass x. And the reaction rate is a y and an x minus y coming together, and the similar loss term. So what I'm going to do is I just substitute into this equation this scaling ansatz and the homogeneity of the reaction rate. And again, this is an elementary exercise, and it's a little bit tedious, so I'm not going to do it in detail here, but do it. It's kind of a fun exercise. And what you'll find is that on the left-hand side, well, this time derivative, well, there's two places the time appears. There's one in the scaling formulation, there is a scaled variable, and then there's time appearing inside of here, and so you do like some simple differentiation, you get this expression for the left-hand side. On the right-hand side, it's a little bit more messy, but it's not anything very fancy. You find that on the right-hand side, everything involves the scaled variable u, which is the mass which is the mass divided by the typical mass of the system. And so if I put these, equate the left-hand side of the equation to the right-hand side of the equation, you see there's some time dependence, some u dependence, and I can separate them out. And so here I've separated out. On the left-hand side is all the time dependence. On the right-hand side is all the u dependence. and they have to be equal, separation of variables from elementary physics classes. And so if I just look at the time dependence, one infers immediately how the typical cluster size varies with time for different homogeneity indices. So for lambda less than 1, one gets power law growth. Lambda equals 1, one gets exponential growth. And for lambda between 1 and 2, one gets a gelation transition at a finite gelation time. And all of this emerges essentially with no work. And by what I mean by no work is you have to have 20 years of experience in knowing how to do this kind of stuff. But it's a very powerful technique that I highly recommend. It's a very natural way to simplify problems. Yes. I mean, when the solutions are described by scaling, yes, it does.
Why isn't there a lambda in the third solution?
In the third solution? Oh, the gel time is a function of lambda. Exactly. Sure. Let me just mention aggregation with input because it's something where if you've seen this picture, if I said I'm now giving a talk about turbulence, and so what's happening here, I'm looking at the energy spectrum of turbulent fluctuations, and so this is the wave number here. So I stick my paddle in the water here, and I make a whole bunch of eddies, and then eddies interact with each other in smaller eddies. They have nonlinear interaction, making smaller and smaller eddies. And I'm asking for the energy density at wave number k, and we know there's a k to the minus 5/3 spectrum for three-dimensional turbulence. You know, I could have all been talking about turbulence here, but this is a problem of aggregation with input in which I'm feeding in monomers at mass 1, and then I have the aggregation process going on. And it turns out that there is a self-similar region where one gets a power law distribution of cluster masses. So there is and this is the analog of the inertial range in turbulence. So let's solve this steady state problem. So we have our master equation as before, but now there is an input of monomers at a constant rate equal to 1. And here I've simplified things a little bit because for constant kernel aggregation, it was 2ck sum ci, and so I've replaced that just by this number density. And again, very simple things you can do. You can sum these equations to get the behavior of the total number of clusters, which goes to 1 in the infinite time limit. So there's a constant density of clusters. One can then use a generating function technique to compute the equation for the evolution of the cluster of the generating function itself. It's a simple equation to solve, and here's the answer. And in the long time limit, it goes to a very simple form that you can then expand in a power series. And bingo, you end up with your cluster mass distribution, power law distribution of masses. So it's kind of a nice example, and it has this nice analogy with turbulence. By the way, how much time should I talk before I say some perspectives? Okay. I think I'll be 5 more minutes. Anyway, so the thing is that this whole kinetic approach, I mean, I've shown it in the context of aggregation kinetics, but one can also apply it to complex networks. And let me show you 2 simple examples. One is something called a random recursive tree, which is a very simple recursive way of generating a complex network. And so the idea here is that you start with a single node. You add new nodes to the network one at a time, and they just attach to any random node in the network. And so you end up with some structure like this, a tree-like structure. And you might ask, what is the degree distribution of this random recursive tree? And using the perspective, this kinetic perspective I've shown you, then, okay, here's the model. And the thing that we want to compute is, in this case, is the degree distribution, the number of nodes of degree k when there's a total of n nodes in the network. And so I want to ask how does this degree distribution evolves. And so here is a master equation in the same kind of philosophy as we've worked out for aggregation kinetics. The basic variable is the number of nodes of degree k, and how does it change every time we add a new node to the network? So here n is like the time-like variable. And there's a gain term. It's now color-coded again because we can attach to a node of degree k minus 1 with some attachment probability, p sub k minus 1. And this will be the gain of nk. There's a similar loss term. There's always an input term because whenever we add a new node, the tail end of the arrow has, by definition, is a node of degree 1. And the thing is that in this random recursive tree, the probability of attaching to a node of any degree is independent of its degree. It's just 1 over n because there's n nodes in the network. And so you end up with this equation. And exercise for the interested student, you can solve these equations one by one, and you end up with a power law, with an exponential degree distribution. One can also apply this to preferential attachment networks. So here we start the same kind of game, except in this case, the rate of attaching to a node of a degree is dependent on its degree. So in this particular case, you'll see that the first node kind of had a little bit of advantage, and we can ask again how the degree distribution evolves in a network of this type. And I'm particularly interested in preferential attachment, where the attachment rate is an increasing function of k. And so again, one can do a master equation approach that's the same as the last slide. The only difference is that instead of a sub k being just 1, it's now proportional to the degree of the node, and so it changes the equation in, at least, it doesn't change the equation formally, but now we have to actually include this. So I'm now just going to skip all steps because this is a whole different talk, but the point is that one can use the whole technology that I've developed in this talk to solve formally for the degree distribution, and there's the answer, the formal solution. And the interesting feature is the asymptotic behavior. And so presumably you've all heard about preferential attachment networks, and when it's linear preferential attachment, one gets a power law degree distribution. The main point here is that this degree distribution is very fragile, and the exponent can be any number larger than 2. And in fact, the robust behavior is in this regime sublinear preferential attachment, where you get stretched exponential, and in the beyond linear preferential attachment, one gets bizarre features where essentially one node is attached to everybody in the network. Okay, so I've come to the end of this presentation. So I've given you a whirlwind tour of a kinetic approach for both aggregation in general, and then a little brief sidelight about complex networks. And so what I see as challenges in my mind, as I've heard the talks earlier today, is that all of these models are based on purely kinetic considerations defining the reaction rates. So things like kinetic pathways, ultrametric structure of the state space, this notion of funneling, that's not in any of this. Is there a way that one can include this in a principled way in some kind of a purely kinetic approach? Because I would argue that the kinetic approach is powerful. It has a whole sort of toolkit of techniques for attacking these equations, for unraveling its asymptotic behavior. So if one has a principled way of defining the reaction rate that includes these features, then one is really in business and making a lot of progress. Let me just tell you two trivial things that we did a long time ago that are kind of in the same direction. So one is the problem of additive polymerization. So in polymerization, one can imagine that you start with monomers, and they make larger polymers, and polymers can aggregate. But one can have distinct reaction rates. Monomers with monomers, the reaction rate of those is distinct from monomers with clusters, and distinct from those between clusters themselves. It turns out that when you allow the possibility that these three reaction rates are distinct, all hell breaks loose in a very amazing way. So this is extremely non-universal behavior. And so that's why I think that including some of these other features here opens the possibility of uncovering new types of kinetic behaviors. Here's another example of a similar ilk. So we called it charged aggregation. So imagine that you have monomers that are either plus or minus charges. They're not physical charges, but just, we can call them red boxes and blue boxes. And you only have bonding between red boxes and blue boxes. And so, for example, you could have and so if you're only allowing bonding between plus and minus, then you naturally have like a linear structure. And so you could have this former, which is neutral because it's got equal numbers of plus and minus, with another neutral, makes something that's even larger. So here the distinction is that you could have interactions between two neutral clusters, K neutral neutral, K neutral charged, or K charged charged. And again, if these reaction rates are different, all hell breaks loose kinetically, and one gets a very rich set of kinetic behaviors. Another feature that is not included in this discussion is the notion of including shape degrees of freedom. My only variable here is the size of a cluster. And in fact, Bob Ziff is the only guy I'm aware of who's actually tried to include shape degrees of freedom in a very beautiful paper 20 years ago where he tried to simulate real cluster-cluster aggregation and try and verify that was the cluster-cluster aggregation process, as done by simulations with real physical clusters that would get larger and would be very fractal in their behavior, was that described in the equations of aggregation kinetics? And surprisingly, it seemed to work pretty well. Another feature is that, as I kind of hinted over here, is that in general, for people who grew up in the field of statistical mechanics, we like to think there's scaling, there's universal behaviors, things don't depend on details. But it turns out that in systems of this type, things are extremely non-universal and very fragile, and it would be nice to try and develop techniques for identifying different behaviors and to actually elucidate them. Okay, I'm done. Thanks for your attention. Yes. Sure.
So if you're trying to build that in a real system, you want the on rates to be distinct in a way that you can't just get by having two different concentrations of blue and red. Right? So if you have different concentrations of blue and red, then some of those rates would be different. It would be more general.
Right. Well, I mean, the thing is that the case that we investigated was equal. I mean, you could. These rates are kind of independent of the concentration, like the concentration has been normalized away from this. So
it's not like I can't think of it as diffusion limited on rate or something.
no, you certainly can think of a diffusion limited process, but the point is that if you want to have equal concentration of plus and minus charges versus unequal concentration, that's an initial condition problem. Those two initial conditions will lead to very different asymptotic behaviors, but it's not changing the reaction rates. But nevertheless, it's an interesting case to consider.
Can't be done in a diffusion limited system. Do that help?
No, I'm not. What do you mean by implemented? I mean,
When you say you give this rich phase diagram or something,
right.
Can I make those rates different?
Yeah, absolutely. Yes.
In a diffusion limited system?
Yes. Well, okay. All I'm saying, in the case where I'm dealing with the rate equation approach, which is the perfectly mixed system, then we've investigated. In the diffusion limited case, no one's looked at it. I mean, it certainly can be implemented, but no one's done it.
So, I have a question. So this seems very related to what Andrew was talking about yesterday, where so this is related to the monomeric addition type of building of the clusters.
Right.
But then there's this other pathway that is described where things are budding out more bulk aggregate.
Right.
But so in all of your cases, you didn't mention, you said you excluded fission, right?
That's right.
Are there kinetic ways to describe things budding out of a liquid bulk?
Well, again, once you include geometry, all of this, this master equation approach just has no way of dealing with this. But if you want to include geometry in the context of saying, well, that's the rate at which, monomers interact with large clusters versus large with large, then you can do it here. And all I can say is that it's an understudied problem that's got a very rich phenomenology. And then the other point you mentioned about fission, yes, you could also generalize these equations, include the possibility of fission. There's a whole, I could give a whole other talk about fragmentation kinetics, where you just take like this table and take it a sledgehammer to and just hit it over and over again for a jillion times and ask what is the cluster size distribution, and then you can marry fragmentation with aggregation. Again, these are very rich problems with rich phenomenology, and I could go on for another 5 hours on these things and tell you lots of interesting stories. Yes?
This is a comment on that, which is, so in principle, you can start with some like Brownian dynamic simulation, and then you can obtain a master equation from it. So we showed that if you do a Markov state modeling approach, you essentially will get a set of states and you measure all the transition rates between them.
Okay.
So then that can be solved as a master equation.
But when you're doing like real Brownian motion.
Real Brownian dynamics, and then effectively you're measuring the transition rates between all of your states.
But will your clusters have any shape degrees of freedom to them, or?
Well, you can choose how you want to decompose configurations into state space, but generally they would. So
Okay.
we used, in one case, a graph approach similar to what Andy showed yesterday. But there are other ways you could do it as well. well. But at the end of the day, however you've chosen to split up your state space, you're then going to have a master equation that describes
Right.
how that evolves in time. And so I would say that this is perhaps more work than you want to do, but in principle, starting from one of these more microscopic simulations, you can both choose how you should be defining your clusters and get the transition rates between them.
Well, again, I think this is also parallel to what Bob Ziff did. I mean, his paper appeared in Journal of Chemical Physics about 20 years ago, and I think it's been underappreciated. But that was a time that so-called cluster-cluster aggregation was hot. So this is a model where you just have Brownian particles, you have a large gas of them, and then they're all sticky, and so when two Brownian particles meet, they fuse, and they just make a little dimer, and then you keep having this thing go continue on. And he actually measured the reaction rates for that process, and bizarrely enough, even though he was doing simulations in 2 dimensions, it seems like it was matching what you get from like this mean field type approach. So it sounds like there's some parallels with what he did and what you guys are doing. Yeah.
People have now thought more carefully about how to systematically define the cluster. So the Markov state model approach, you're using the kinetics to tell you how to define the clusters.
But how your cluster is defined is not mass the metric you define a cluster?
So you make a graph of how the things are attached to each other, but then that leaves you with a whole ton of graphs.
Oh, so you're saying like each lattice animal that's created is its own cluster, and you're enumerating all of the different possibilities.
I don't really want to do that. That's a lot.
Yep.
Then what you do is the graphs, which your kinetics show you are rapidly interconverting, they get lumped into a single state.
Okay,
And then what you're interested in is the rates of transitioning between those states.
I see.
So this is exactly what was done in protein folding, but as Andy showed, the complication for these aggregation things is that you have these interchangeable subunits. So one needs a different way of defining them.
Yeah, this, as you point out, this is like a principled way of like trying to build a master equation from like microscopic simulation. It sounds really cool, and yeah, I'd like to know more myself about it.
So if you added fragmentation as another linear term, the generating function would just would go through easily.
Well, there's actually a little bit of subtlety in including it, but yes, in principle, it's a well-defined, a well-posed mathematical problem. Can you actually solve the resulting equations? You can in very specific cases because you have to also now include some fragmentation rate. And so depending on the nature of fragmentation rate, you can get something which is tractable or you can get something which is impossible.
And scaling methods?
I've not applied that same scaling approach to like combine aggregation fragmentation, but I don't see any reason why it wouldn't work. The thing is that one thing that simplifies aggregation fragmentation is that often you're driven to a steady state. Once you're dealing with a steady state, like it's a lot simpler. But yeah, that'd be a fun thing to do. Yes.
If you can implement, you can explore that phase diagram for charge aggregation with DNA strands, because from what I understand, the unweights, if you have two long DNA strands with a given amount of time together, a given number of matched base pairs, the actual kinetics of how fast they have to get the non-weight depends on can we vary because of some deviation physics. The first and second is matching base pairs affects how quickly they come together, even if the actual binding energy is the same.
Right.
Tell us a little more about this. Then you could actually implement all the things you're saying. You could have the red and blue line really fast because they have
Whether they're matching or not, yeah.
But there would be two distinct binding sites on the blue line.
Yeah, again, the one thing I would say is that, if I think about like the aggregation process, I have this reaction rate matrix, Kij. And constant kernel aggregation is where Kij is every element of the matrix is constant. If I do something where I make like one infinite row, like one value, and another infinite row, another value, like all order one, but different values, that's the case where the system is incredibly fragile. And I can imagine, and I know for a fact, because I've solved some of these cases, you get very weird behavior. So if you have like a principled model like this DNA aggregation process where you have some principled way of saying like what are the different rows or columns of the matrix, it sounds to me like a cool problem, and I'm sure it would have interesting kinetics. Yeah.
My point is just that I think DNA on rates can be predicted by sequence, right?
I think the nucleation is limiting. So like when they first bind, that's the most fast that you get, and then when they zip up, that's kind of
Right, and depending on how big the sequence allow in the sequence, that's slow step, the rate of that slow step is between.
yeah.
I mean, if you're holding at some temperature where it's stable-ish, but it might come apart, that can be very finely tuned by controlling the
length of the
length, just the sequence that you get. You know, this is inaccurate. Don't call me on the Sean. GC is roughly like twice AT. Caveat. And so I know that twice energy can matter a whole lot. I mean, you can change the temperature that they would melt that by just several degrees.
But, I mean, just if I can pick up on your comment, I mean, the problem of equilibrium polymerization was solved in 1944 by Blatz and Topolsky. So they studied the problem of constant kernel aggregation with constant fragmentation rates everywhere, and you end up with, not a surprise, exponential distribution of polymer lengths. But if you're saying that in the DNA problem you have like aggregation rate that AT, GC are the factors of 2 floating around between different elementary reaction rates, and then you want to ask, like, what is the equilibrium distribution of such a system? Because of my experience here with this additive polymerization, I can imagine the results are very fragile and very dependent on those ratios of rates. It might be an interesting problem to take a look at.
Yeah, I mean, the point I was making is that if you want them not to be constant, you do actually get fairly fine. You have pretty good energy models.
Okay.
And you can say, I'd like this to be 1.1 times stronger, or you can actually swap in a sequence and it seems to match.
Yeah, so then I would argue that the equilibrium size distributions could be very, very dependent on that 1.1 factor.
Yeah.
Which, I don't know if that's well known or not, but that's...
I grow polymers out of DNA, and it matters a whole. I mean, I'll switch from one. We use PCR machines
Yep.
for it to hold it, and I'll switch from one machine to another, and they're calibrated differently. This one, they say they're both 53C, but that one's actually 52.7. So, yeah,
Okay.
it's very fragile.
I see.
Temperature, and they're both binding strengths. I have lots more questions, but I don't know.
Well,
I'm going to corner you.
okay, we can fight at lunch.
Yeah, it might be interesting to look at where we can design and actually implement in the test tube nanostructures that get you into the kind of math-friendly regime.
Right.
So I think you can, if you're looking at the hybridization, the folding, it's similar to maybe protein folding, but simpler, and you benefit from dealing with geometry. But we can start to build, once we already are good enough at making those shapes that we can actually fold those into monomers that would more resemble these kind of red and blue tiles, and,
Okay.
and then look at those coming together. So I think that's where we could probably get the most mileage initially. It's just kind of not worry about the complex, really,
Right.
sophisticated.
No, I mean, I'd be really pleased if someone can make a system like this because, we worked hard on it. I mean, it was one of the most complicated mathematical papers I've ever worked on, and it's like nobody notices it because it's kind of like mathematical bullshit until there's actually a physical realization of it.
I think people have already done this and probably not cited you. That's why I said
Okay, could be.
But maybe.
Because this is 30 years ago, so that's So it's a favorite of mine that no one knows about. Yes.
This might be a very stupid question, but I think I was able to follow most of that derivation of this mean field solution, but I have no idea how you would include shape degrees of freedom. Could you just give an example of how you...
No. That's not a dumb question. That's a hard question. I have no idea myself. I mean, one way you could do it is kind of like along the way that Mike was mentioning, is that you could enumerate, if we're dealing with, say, clusters in 2 dimensions and they're kind of rigid and they make little lattice animals, so these are connected clusters that are kind of like sort of conforming to a particular lattice, and you could then try to figure out, like how many, what's the size of the perimeter, and maybe the reaction rate is some function of the perimeter of the cluster rather than the mass of the cluster. But nothing has really been worked out in any reasonable way. So that's a hard question, not a dumb question.
much different model, but I would say kind of approaching this level, like, very simplified, but trying to bring in, physical principles, but in the shapes we think about are so that everybody's, we draw it like a square, and then it's got 4 binding sides of lines and a square lattice. But yeah, it really felt like we were just making up the physics along the way.
But I mean, it just seems like one thing which would be fairly simple and possible is just to say that if I'm thinking of like a tiling lattice animal and a square lattice, just say that the reaction rate is not proportional to the mass, but it's perimeter. And the average perimeter is not known exactly for lattice animals, but one can enumerate, one can get a good idea of the scaling behavior of it. It could be an interesting problem, just that alone.
We had an interesting system with some cheap dependence because they're almost like 5 rules. So this analyte 5 rule type thing is coming together.
I'm sorry, what rule did you say?
Like analyte 5 rules, like in Alzheimer's.
Okay.
Peptides that come together and make these horrible things in your brain. When you have oligomers, it's very easy for a new monomer to come along and stick to it. But when they get sufficiently long, they self-organize into beta sheets, and monomers can only stick on the ends. And so there seems to be a regime change in this homogeneity index that is 1 when you're small, it's lambda. Becomes, I think, less than 1 actually.
Okay.
You're large. So that was a very simplistic way of incorporating some.
I see. No, we should talk at lunch about that. That sounds really cool.
I've actually delayed.
There's some nice tricks, sir, I haven't seen before.
Okay.
A copy of your slides, please.
Oh, sure.